All right, welcome back. Today we're going to take a look at binomial distributions, and I want to put a big precursor on this one. This is the basis of this unit. If you don't understand binomial distributions, the rest of the unit will kind of be lost on you. So this lesson is fundamental to understanding the next three lessons. Please pay close attention and try and do your best. And if you're having trouble with this one, get help immediately. Do not wait, because it's too important to understand this before you move on. Okay, just before we get going, I'm going to remind you that a couple units ago, or last unit, or whatever it was, we took a look at a binomial expansion, which basically means we take a plus b to the exponent n for some value of n. So the a plus b is the binomial, the exponent n is why we need to expand it. When we did that, we got out a formula. It was the, what do we call it, the binomial theorem. And we did see in the binomial theorem that there was this equation, which was our general term. The r plus first term, remembering that r starts at 0, but of course when we're counting terms, they start at 1, is equal to a combination, and then the first term to an exponent, and the second term to an exponent. Now, for example 1, if you can just kind of follow along and get the gist of it, don't worry too much about remembering the exact numbers to plug in anywhere there. I just want you to kind of get a feel for how what we're doing today with binomial distributions is related to the binomial theorem, other than the fact that, they both have binomial in the name. So what I've done here is I've made a tree diagram, and I used an actual tree diagram generator. That was surprisingly hard to say. A tree diagram generator to produce this. And it's a pretty simple one. Now it's got a stochastic process on it, only because it's got the 1 in 6 chance of, in this case, rolling doubles, or a 5 in 6 chance of not rolling doubles. And then at the end of each of the branches, I've put in the probability that that branch is followed. So for instance, the very top one, the probability that I roll doubles 3 times in a row is 1 out of 216. It's 1/6 times 1/6 times 1/6. And then all the other probabilities are there as well. So using that idea, I made this little very short probability table that shows me the probability of rolling 0, 1, 2, or 3 doubles. Now, a few of them, for instance, the 1 double, 75 out of 216. You'll notice that's not one of the outcomes. It's actually 3 of the outcomes all added together, because there are 3 ways to get that. But either way, that's it. That's the probability distribution for rolling doubles if I roll a pair of dice 3 times. So far, so good. Again, don't worry too much about calculating all these numbers. It's the idea of this example that's more important. It's also the reason that I have everything filled in already instead of doing the math as we go, just to save a little bit of time. Okay, now as a completely separate process, let's take the binomial 5, 6 plus 1, 6 to the exponent 3, which I think everyone can probably figure out is going to equal 1, because 5, 6 plus 1, 6 is 1, and 1 cubed is still 1. But instead of actually figuring out what that is by completely evaluating it, what I'm doing is I'm just going to actually separately evaluate all the separate terms in the binomial expansion. And again, if you forget how to do these binomial expansions, go back to the binomial theorem that we covered in Unit 3. So when I do that, you'll notice I get 4 terms in my answer, and I could add them together to get 1. But rather than do that, I'm just going to focus on the fact that the numbers there are 125 over 216, 75 over 216, 15 over 216, and 1 over 216. Now, looking up at the probabilities I got when I did my tree diagram, they're exactly the same numbers. And we want to abuse that fact to do probabilities when we have a binomial that we have to expand. So this is where binomial distributions meet binomial theorem. Come on, go small again. There we are. Okay, there's some details there about what all the numbers represent. Don't worry too much about that yet. As we get into the actual examples where I do the math with you, we'll worry about doing them. What I will point out, though, is that the numbers in the binomial expansion there, the 5/6, 1/6, and 3, The 5/6 is the probability of not getting doubles, the 1/6 is the probability of getting doubles, and the 3 is the number of trials that I did. I rolled to try and get doubles 3 times. Okay, so those numbers are highly related to the actual problem with the dice. The next idea I want to talk about quickly, well, I'm going to say quickly, but we're going to keep driving this home because it's important to understand this, is the idea of repeated Bernoulli trials. This is just a fancy name for a relatively simple idea. So it turns out that our binomial distribution will work as long as we have something called repeated Bernoulli trials. And a repeated Bernoulli trial is any kind of trial that we're doing, any kind of experiment we're doing, where each time I run the trial, it's identical to the trial before it, not necessarily the outcome, but the trial itself. So for instance, in the last experiment, we rolled a set of dice, so we rolled 2 dice, and we looked to see whether or not we got doubles. And then we rolled them again and saw whether or not we got doubles, and then we rolled them again and saw whether or not we got doubles. So those were identical experiments. The second criteria for repeated Bernoulli trial is they must be independent of each other, meaning the outcome of one will not influence the outcome of the next. Similarly, when we're rolling the pair of dice, the outcome we get on the first one, whether it's doubles or not, does not affect whether or not the next one will be doubles. It's not like we, rolled a double and now we're all out of doubles. We can't do doubles anymore. We still have the exact same probability of getting doubles the next time, completely independent. And as you might guess from the idea that it is a binomial distribution, binomial means 2. We can only have 2 outcomes to the experiment. Now, I realize when you're rolling a set of dice, there are actually 36 outcomes. You can roll a 1 and a 1, a 1 and a 2, a 1 and a 3, a 4 and a 5, a 4 and a 6, etc. However, if we break the experiment down to make it simpler, really in the experiment we did, all that mattered was we got doubles or we did not get doubles. And those were the 2 outcomes. And we will normally refer to those as success and failure. We got what we wanted or we did not get what we wanted. So those are the 2 outcomes. Okay, I'm going to keep driving that home because it's important to understand that for the next few lessons, because some of the other distributions require repeated Bernoulli trials and some require that they are not repeated Bernoulli trials. So understanding a repeated Bernoulli trial, kind of important. 3 criteria: identical, independent, 2 outcomes, success and failure. Okay, so if we meet those criteria, then when we do these experiments, we have a binomial distribution, and we have an equation for that. Now, this is the equation right there. The probability that x equals n choose x, p to the exponent x, q to the exponent n minus x. So just to be clear, if you look at the form of that, a combination, something to an exponent, something to an exponent, that looks an awful lot like the general term that we got for the binomial theorem. We're using kind of different variables and setting it up slightly differently, but it is that same form. A combination, something to an exponent, something to a different exponent. And specifically, those two exponents add up to be n. And for our version, they will also add up to be n. We're just using an x instead of an r. Okay, so what we're going to do is say that x is the number of successes, and then n minus x, I think you can guess, is going to be the number of failures because it's all experiments minus successes. Oh, I just realized, not that it's a huge deal, but I should be more consistent. This should be a lowercase p. And since it's hand-drawn, it actually looks pretty much exactly the same anyway, but it should be a lowercase p. P plus q, probability of succeeding and probability of failing, should total 1 or 100% because they're the only 2 possible outcomes. So if we know one, we know the other. Okay, so just to kind of explain where the equation comes from, which hopefully will make sense. If I do an experiment a bunch of times, the probability of success should occur x times if I have x successes. So that's why we say, we had 1 success and another success and another success until we have x of them. And that means that the probability of failure must be to the exponent the number of failures, which is all of the experiments minus the number of successes. And then the n choose x part at the beginning is really just saying, where do those successes occur? So if we did the experiment 3 times and we got 1 success, does it occur on the first, second, or third? Well, that happens in 3 choose 1 ways. If there are 2 successes, it happens on the first and second, first and third, or second and third. 3 choose 2 ways is also 3. So the first part tells us where the successes occur, and then its probability of success to the number of successes, probability of failure to the number of failures. Okay, so what looks like a kind of nasty equation actually is fairly straightforward to use. And by the way, I don't memorize it as variables. I remember it as kind of like what it is. It's the number of ways of choosing where the successes occur, probability of success to the number of successes, probability of failure to the number of failures. So example 2, find the probability distribution for the number of correct answers on a multiple choice quiz that has 4 answers to each question and 3 questions, assuming that we're random guessing. The random guessing is to assure that all outcomes are equally likely. And anyway, yeah, let's give this a shot. So we want the probability distribution. Now I could use x equals x, but let's pick a, for now let's use x equals x. And I'm going to remind you this is number of successes, which in this case is going to be correct answers. Okay, then we've got the n choose x. So we have 3 questions. We have to figure out where the correct answers are going to be. So that's going to just be 3 choose x. The probability of success, the probability of getting a question correct is 1 in 4, since there are 4 answers and we're randomly guessing which one it is. So there's a 1 in 4 chance of succeeding, and x is the number of successes. And then the probability of failing, 3/4, to the number of failures, which is going to be 3 minus x. X successes, 3 questions in total, 3 minus x failures. Okay, at this point we could evaluate the 4 possible outcomes. Why don't we do that kind of quickly? So the probability that x equals 0 is just going to be 3 to the 0, 1/4 to the 0, 3/4 to the 4, to the 3. 3 questions, 4 answers each. Okay, when I plug this into my calculator, 3 choose 0 does nothing. That's just 1. 1/4 to the 0 does nothing. That's just 1. So we just type in 3/4. So 3 divided by 4 to the exponent 3. And that's 0.42, or I could write that as 42, and it's going to round up to 42.2%. Now I can do the probability that I get 1 correct answer. Just 3 choose 1, 1/4 to the 1, 3/4 to the 2. Now this time I have to plug a little bit in. So 3 choose 1 is just 3 times 1/4 times 3/4 squared. And I'm getting 42.2% again. Is that a coincidence? Kind of, yeah. These do come up quite a bit though. Just to be clear why that worked is because when we moved our exponents, when we moved the exponent from 3 there and 0 here to 2 and 1, the only difference is the bottom's still the same. It's still 4 to the exponent 3. The top is now 3 squared instead of 3 cubed, but we added another 3 in there, so that compensated and we get the exact same mathematical answer. Now that doesn't mean the next 2 are going to be the same. Let's see what happens. Here we have 3 choose 2, 1/4 squared times 3/4. Okay, so 3 choose 2 is just 3 times 1/4 squared times 3/4. And I'm getting 14.1%. One outcome left. 3 choose 3. There's only one way that I can have 3 successes. That's success, success, success. 1/4 to the exponent 3 and 3/4 to the exponent 0. Now, just before I go anywhere, if I look at the 3 probabilities that I've already worked out, the first two is 84.4, 98.5. I'm assuming this is going to be around 1.5%, but let's see if that's actually the case. Okay, so 3 choose 3 is 1. 1/4 cubed. Oops. 1/4 cubed. And then 3/4 to these 0 is 1 as well, so it does nothing. And that rounds off to, 1.6%. Okay, and just a little check there. If I add those up, I do get 100.1%, which of course is not possible, except that really we know that all 4 of those were rounded off. So that extra 0.1 is really just a little wee bit of rounding error. Nothing to concern ourselves with. Okay, so despite the fact that the equation looks kind of nasty, I think once you've used it a few times, it won't be a matter of you'll memorize it. It'll be a matter of you understand it enough that you don't really need to look it up. It's just a combination, probability of success, number of successes, probability of failure, number of failures. I realize I may have said that 2 or 25 times so far, but that's one of those things to just really drive home, because if you get this one, the next few lessons are relatively straightforward. Okay. So I thought I would just put this in here for a brief explanation because, yeah, we have a new theorem or a new distribution equation, I should say. Is it really better than just doing the tree diagram? And what I did here is I just put down some examples. So if our number of trials is 3, so we, in our example, flipped 3 coins, our tree diagram had a total of 8 branches, and the total number of terms in the binomial expansion was 4. Okay, that wasn't too bad. I suppose we probably could have done a tree diagram just as easy as the binomial expansion. But as the number of trials increases, you're going to see that what happens is the tree diagram becomes impossibly difficult to draw. In fact, I'm going to say it is impossible to draw. I'm not even going to say it's theoretically, it's literally impossible to draw. There is no amount of time or space that you could have that you would ever be able to make this tree diagram with 1,000 trials. Now the binomial expansion is a little bit time consuming as well. It does have 1,001 terms, but that's possible. It'll take you a while, but you'll get there. We did 4 of them in about 2 minutes. I'd say you can do 1,000 in, let's say, 500 minutes. So within one decent day, you could do this one in about 10 hours probably. And after a while, you'll probably get a little faster. But just to be clear, if we look at this number right here, I need to try and put this in perspective. The reason I say that it would be impossible to draw that tree diagram is because 1 to the exponent 100 is bigger than the number of atoms in the universe. Now, some people will look at this and say, wow, so 1 to the exponent 100 is the number of atoms in the universe. 10 to the 300, that's 3 times bigger. No. That's 10 to the 200 times bigger. That's if there was 10 to the 200 universes, there wouldn't be enough atoms to make this diagram. 10 to the 200 universes. So what that means is if every atom in our universe blew up and became its own universe, and then every one of those atoms blew up and became its own universe, there would still not be enough atoms to make this tree diagram at 1 atom per branch. That's why I say it's completely impossible. It's not even theoretical, it's completely impossible. Okay, now that I've really driven home why we don't want to draw tree diagrams anymore, the binomial expansion is not actually that painful, so let's just use it. Okay, let's do expected value for binomial distributions. Okay, so for example 3, we're using the definitional equation for expected values, calculate the expected number of successes that you'd get from guessing all 3 questions on the multiple choice quiz. Okay, so remember that equation, as nasty as it seems, was really just equal to the sum of x times the probability that x equals x, which is a fancy way of saying take all the outcomes, multiply them by the probability they occur, and add those all together. So if you forget that equation as that notation, that's not a big deal as long as you understand the idea behind it. Okay, so there were 4 possible outcomes that we had last time. So the first one, there was 0 successes, and that happened 42.2% of the time. And then we had 1 success, that also happened 42.2% of the time. 2 successes happened 14.1% of the time, and 3 successes happened only 1.5% of the time. Or sorry, 1.6%. We did round that one up. Okay, so I'm going to work these out, and I'm going to convert all of these percentages as I'm doing them into decimal numbers, because remember that expected value is not a probability, it's not a percent, it's a number of correct questions. Okay, so the first one I can do in my head because that's 0. The second one I can do in my head because it's 1 times something. The next one is going to be 28.2% or 0.282. And the last one is going to be 3 times 1.6%, which is 4.8% or 0.048. Okay, and now I'm going to pull out my calculator because honestly, I just lose track of numbers in my head. 0.048. And I get 77 or 0.772. 0.772. So if I did this experiment, I'd expect to get 0.772 questions correct. Now I'm going to point out that there is an equation here that actually is a little bit easier to use. It's just that one. Now this only works for binomial distributions. It's actually not strictly true. We'll see that it does work for another type of distribution as well. But for our purposes right now, we have to kind of realize that expected value equations are dependent on what kind of distribution we're using, much the same way our probability equations depend on which kind of distribution we're using. So it's just equal to n times p. Well, that's a much easier equation to solve than that one, which was just kind of a pain in the butt. And for this example that we just did, that was just be n is the number of trials. There were 3 trials. And the probability of succeeding in any given trial was 1 in 4. So that's just 3/4 or 0.75. So we'd expect to get 0.75 questions correct. Now you will notice, of course, that that is a little bit different than 0.772. Turns out that not only is the second equation easier to use, it's actually more correct. The reason for that is that our first equation, all of our percentages that we used, all of our probabilities, were rounded off. So that one actually does have rounding error. Not a huge amount, but enough that it is different. The correct answer is 0.75. Now, if you think about what that equation is really saying, it's just saying 1/4 of the questions are going to turn out to be correct. There were 3 questions, so 1/4 of 3. That seems super obvious, that would be the average number of correct questions. Okay, now I will point out again, I'll try to keep pointing this out. Expected values are not what we actually expect to get on any given trial. I will never write this quiz ever and get 0.75 marks out of 4. It just does not, or out of 3, I should say. It will never happen. It's not a possible outcome. It's just the average if I did the experiment a billion times and said, okay, on average, what did I get on this quiz? So let's just do a few more examples so we become a little bit more comfortable with this. Once we're comfortable with this, we're really set for the rest of the unit. So question 4, a pair of dice are rolled 20 times. Now I'm questioning the grammar on that. English people, help me out here, even though it's a video and I can't possibly hear you. A pair of dice are rolled or is rolled? Because are would be for plural, but there is multiple dice, but there's only 1 pair of dice, so that would be a singular pair. I think that should be is. Is? I don't know, and frankly, I'm a mathematician, so I don't care. Let's just try the problem. pair of dice is or are rolled 20 times. Find the probability of rolling doubles exactly 5 times. I'm going to just do a little aside here. The probability of getting doubles is 1 in 6. I could do a dice table and try to prove this to you, or you can kind of just logic your way through it. But the first die I roll can be anything. So there's a 6 in 6 chance it will come up as a number, and then there's a 1 in 6 chance the second one will match it. So that's just a 1 in 6 chance of getting doubles. Or you can think of it as there are 36 possible outcomes, and 6 of them will be doubles, double ones, double twos, double threes, etc. Either way, probability of doubles is 1 in 6, and we're going to need that because it's one of the variables that we use in our actual binomial distribution equation. Okay, so we're doing 20 trials. So let's do probability that doubles equals 5. We're looking for the doubles criteria to be met 5 times. Well, those 5 successes are going to occur somewhere in those 20 rolls. That's where the first part comes from. 20, choose 5. And then we have our probability of getting doubles, success, to the number of successes. And then our probability of failure, which is obviously 5, 6, to the number of failures, 15. Okay, notice that at no point did I really refer back to the formula and say what is X, what is P, what is Q, where does all the different things go. The combination, probability of success to the number of successes, probability of failure to the number of failures. Okay, now on this one, I'm going to show you a little, well, I'm going to verbally say a little trick. It's going to look the same when I write it down. But I'm going to do the 20, choose 5. And just sometimes you might find this a little easier to punch into your calculator. If I think of the numerators and the denominators separately, the numerators are 1 to the exponent 5 times 5 to the exponent 15, which is just 5 to the exponent 15. So I'm going to multiply that by 5 to the exponent 15. And the bottom is going to be 6 to the exponent 20, because there's 5 of them from the first fraction, 15 from the second fraction. So 6 to the exponent 20. Oops, I think I punched it in wrong anyway. Let me try that again real quick. Okay, that's better. And I get out 0.129, which is 12.9%. Okay, so not too bad. Now, of course, you're welcome to calculate that however you'd like in your calculator. I just find it, rather than put a fraction into one exponent and then another fraction to another exponent, I just do the numerators as 1, because one of them is usually 1. I won't say it's always true, but usually. And the bottom is just 6 to the exponent 20, since it's 6 to the exponent 5 times 6 to the exponent 15. Could save you a little bit of time and slightly less likely to make an error in your calculator. The good news here is that usually when you make an error on your calculator, it's a ridiculous number, because you're multiplying when you're supposed to divide or something like that, and you get numbers that don't make any sense whatsoever. Okay. What is the probability of rolling at least 2 doubles? Ooh, okay, this one's going to be a little bit different. Just a little bit, not too much. So probability of at least 2 doubles. How do I write that? Well, at least 2 doubles means that doubles has to be greater than or equal to 2. So now I have an inequality in there. That doesn't really change anything. I still understand what that means. And there's a couple ways I could approach this question. I could say, what's the probability of getting 2 doubles? What's the probability of getting 3 doubles, or 4 doubles, or 5 doubles, or 6, or 7, or 8, or 9, or 10, or 11, 12, 13, 14, 15, 16, 17, 18, 19, or 20? And the fact that I slurred those together because I was so sick of just saying the cases is a good indication that I don't want to calculate it that way. So really what I want to do is just say that that's equal to 100% minus the probabilities of the things I don't want. So at least 2, the only 2 things that don't count here are the probability I get 0 doubles or 1 double. All right, so when I do that, unfortunately now I have to use the binomial equation twice. The good news is it's not actually a hard equation to use. So the first one is just 20, choose 0, 1, 6 to the 0, 5, 6 to the 20. And the second one is 20 choose 1, 1/6 to the 1, 5/6 to the 19. All right, so the first one there, the good news is the first and second factors don't actually do anything. They're both ones. So it's just 5/6 to the exponent 20. And that, as a percentage, is 2.6%. I could keep more than one decimal if I wanted to, but I think that it's good enough. We don't bother with that. And then the second one is 20. 20 choose 1 is just 20 times 5 to the exponent 19 divided by 6 to the exponent 20. And that's going to be 10.4%. Okay, so now that's actually not too bad to calculate. So we do 100 minus 2.6 minus 10.4, and that gives us an even 87%. I'm going to actually write it as 87.0, just to remind myself that I did actually keep one decimal place accuracy, and I know what it is, even if it is a 0. Okay, so that wasn't too painful. We just had to solve it using the same kind of indirect reasoning that we've been using for a few units now. Okay, what about the expected number of doubles that we'd roll? Again, not the number that we're ever going to necessarily get, but if we did it a million times, what would the average number of doubles be? So the expected number of doubles, we have a really easy equation, n times p, which is just the number of trials, times the probability of getting success in any one trial. And then 20 divided by 6 is just 3.3 repeating. And I'll keep 2 decimals there because I feel like it. Okay, so again, I'm never going to roll 20 dice and get 3.33 pairs, but on average, if I did it a million times, I would expect to get something around 3.33 pairs. Okay, hopefully this is starting to become a little bit more comfortable for you. Let's just do a couple more, moving away from dice and those simple problems. So here's sort of a real-worldy type question. Of course, there's always a little bit of fictitiousness in these because we have to do the math class stuff, but this is a type of question that might actually be applicable in the real world. So when making an LED TV, it is found that 0.1% of them are defective. If a store orders 25 TVs, what is the probability that they'll get at least one defective TV? Okay, so we want the probability. I'm going to use D for defective. At least one means it's going to be greater than or equal to 1. So at least one defective television. Now, before I go any further, these types of questions right here, this one specifically, tends to confuse students for one really tricky little reason. It has nothing to do with the math. It has to do with English. Our equation is set up for probability of success and probability of failure. What makes this one a little bit tricky is that success is a defective television and failure is a working television because it's the thing we're not looking for. And because of that, a lot of students want to associate the positive outcome, the outcome that they like, which would be having a working television, as successful, and a non-working television as failure, but that's not how we're defining them within this question. We're defining defective as being the success criteria. I know it's weird, but that's the way it is. So just make sure you're keeping track of that in questions where the thing you're looking for is actually a bad thing. Okay, probability that one or more is defective. And that should just equal 1 minus the probability that 0 are defective. Unless you want to do this one directly, in which case you're welcome to, you just have to work out the 25 binomial equations. But I'm going to do it indirectly because I think it's a little bit faster. Oh, I will point out this time I wrote down 1 minus instead of 100% minus. They're really the same thing. It depends on whether you want to work in decimals or percents until you get to the final answer. I actually usually work in percents, so I'll just change that right now. And then the probability that defective equals 0, means of 25, I have 0 defective. The probability of success is the probability of being defective, which is 0.1% or 0.001 to the number of defective. I will point out that the other common error I see on questions like this one is people who just move the decimal place wrong for 0.1%. And then the probability of failure, which oddly enough is a working television, is 0.999. And we expect to have 25 of those. Or we, for this purpose, want 25 failure working televisions. Sounds weird. Okay, so the good news is the first and second factor are actually ones. They don't do anything. So all we have to punch into our calculator is 0.999 to the exponent 25. And that works out to be 97.5%. And you know what? I'm going to keep one more decimal, I think, this case. 53%. And so the probability that I get at least one defective television will be the difference of those, which is going to be 2.47%. Okay, so despite the fact that only 1 in 1,000 televisions is actually defective, if I have 25 of them, there's a 2.47% chance that I have at least one defective one. Not bad odds. I'll take them. I'll take those any day of the week. Incidentally, I've bought like 6 LED TVs, I think, in my life, and 2 of them were defective, so I'm not having great luck with those as far as statistically goes. Actually, I shouldn't say that, because my last one, they couldn't fix it. They had to replace it with a better model. It's awesome. And they gave me a $100 gift card. It's pretty cool. Maybe I am lucky with TVs. I changed my mind. I retract my statement. Okay, one more. A game consists of rolling a pair of dice 10 times. Each roll where the dice sum to 6, 7, or 8 awards the player $1. If it costs $5 to play the game, is the game fair? Okay, before we get too far, let's unpack that last part. We already saw that a fair game means that the amount you win on average, the expected amount of winnings, should equal the amount that it costs to play. So really what this is saying, despite the fact that it's not saying it, is figure out what the expected winnings are and then see if it's equal to $5 or not. That's really what the question is asking. Okay, the first thing we have to do is figure out what the probability is of rolling a 6, 7, or 8 on a pair of dice. Now, you recall that there's that dice table that we make here, and just for time's sake, I'm not going to actually draw the whole thing, but I'm going to remind you that if you actually think about it, you always get 7s across the diagonal here, and you're going to get 6s right above them, and you're going to get 8s right below them. Oops. Fix that one there. I put it in the wrong box. Okay, so when I do that, I end up getting a total of 6 plus 5 plus 5 is 16 out of 36 that meet the criteria. And I could convert that to a percentage. However, because these are going to get often fairly large exponents on them, I don't know if I want to put that too approximated, because even a slight approximation with a high power on it is a bad thing. But I think I can at least put it in lowest terms. So that would be 4 over 9, I believe. And I think I want to use that number in my equation. Okay, so the expected number of wins of my 10 dice, keeping in mind each win will yield $1. So the number of wins and the amount I win are actually the same thing in this case, the same numeric value. Should just be the number of trials, which is 10, times the probability of success, which is 4/9. So 10 to the exponent, 10 times 4/9 is 444. So Again, depending on how we consider this, you could consider this to mean that we're going to get one of those numbers, 4.44, out of the 10 rolls. Or you can think of this as because each success is $1, you can actually think of this as $4.44 per play. Now, because I did put down the expected amount of winnings, I'm actually going to put down the dollar version. If it was $2 to play, I'd have to double that. I would have to say there's $2 for every win. Anyway, it doesn't matter. So is this game fair? Costs you $5 to play, and on average, you're going to win $4.44. So it is not quite fair. It's not way off, but it's close. And by the way, this is the kind of casino game that you might see out there. Not this one. This one's actually a little oversimplistic. But the idea of most casino games is to make games that convince you that you have a good chance of winning money, despite the fact that you never do. There's no casino game out there that on average pays out more than it takes in. It just doesn't exist. So the goal is to make you think that you're going to win often by giving you something that sounds good. Well, you win if you get a 6, 7, or 8, and you can play, and you've got 10 chances of your 10 rolls. But realistically, you'd have to win 5 of the 10 to break even. So maybe not so lucky. Okay, I think I'm going to stop there. Again, this was pretty much one of the biggest ideas in this unit. So I do want to give you some time to absorb that and try some questions. And then in our next few lessons, we're going to take a look at a couple of distribution types that are related to the binomial distribution. They're not the same. One of them is kind of its partner. It's very similar, but it solves for something different. And then the other kind that we'll look at after that is basically its counter opposite, its nemesis, which is the opposite of binomial distributions. But you have to understand binomial distributions to understand what the opposite of it is. So give the homework questions a try. Let me know if I can help in any way, and I will see you in the next lesson.